Hello. Today we're going to be covering Putnam 1985, problem A5. So this problem is asking us, we have the integral of a product of these cosine waves of integer frequency 1 through m over the period 0 to 2 pi, for which integers m is this integral non-zero. And so glancing at this integral, it's clear that for m equals 1, the integral from 0 to 2 pi of cosine of x dx is simply equal to 0, because we're integrating cosine wave over its period. And also for m equals 2, if you're familiar with a little bit of partial differential equations, you'll remember from the orthogonality condition of cosine waves that the integral from 0 to 2 pi of any two cosine waves of different integer frequencies is always 0. Okay, so that's an important relationship known as the orthogonality condition, and that can be proven using brute force, using using a basically integration by parts. You can also prove it using complex analysis. And so attempting this problem, I first kind of did a bunch of brute force for m, m equals 3 and so on. I was doing some brute force calculations using integration by parts. And I found that it was very difficult to come up with a decisive solution, even for m equals 3. So if you're interested in those types of things, you might as well want to try m equals 3 by hand, just using, basic integration techniques. But I found it was very, very difficult and certainly could not do it in a good amount of time on a Putnam exam. And so then I had the idea to basically use complex variables and substitute what we know to be cosine of x. So first of all, complex variables gives us the formula e to the I theta is equal to cosine of theta plus I sine theta. And this is Euler's formula. It follows by definition, but also by the equivalence of the Taylor expansion. And so using this identity, we can write cosine of x as 1/2 of e to the ix plus e to the negative ix, okay? And similarly, for any integer frequency cosine mx, I can write this as 1/2 e to the imx plus e to the negative imx. And so let's rewrite the integral I sub m is equal to the integral of these cosine waves, cosine of x, cosine of mx. Let's rewrite this in terms of complex exponentials. So I have the integral from 0 to 2 pi of 1 over 2 to the m. I'll just pull out all the factors of 1/2 immediately. And then e to the ix plus e to the negative ix times e to the I2x plus e to the negative I2x, all the way to e to the imx plus e to the negative imx dx. Okay? And now we have an interesting integral. So now we're integrating a complex function, and it's clear that we're integrating over some sort of angular coordinate because we're integrating x from 0 to 2 pi. And so that tells me that I want to try and make basically a u substitution and change this differential. So if I was integrating, for example, f of z dz along a circle, a unit circle, I would make the substitution f of e to the I theta I e to the I theta d theta, okay? And this is just basic rules of parametrizing a line integral for complex analysis. And so looking at this substitution, it's clear that I have a d theta in my dx. And so I want to basically pull out a factor of I e to the I theta and then backwards substitute to get a function in z, which will end up being a polynomial. And so it'll be nice to work with. Okay, so let's do that. So I'm going to pull out the 1 over 2 to the m. And then I have the integral from 0 to 2 pi. And now I'm going to pull out an I e to the I x. And I'll bring, to account for the I, I'll just bring an I outside on the denominator. And then the e to the ix I'm going to take from this first term here. So it'll be 1 plus e to the negative I2x. And then everything else in the integral will stay the same. E to the I2x plus e to the negative I2x all the way to e to the imx plus e to the negative imx. And now we have something very nice, because now I've done the proper, I've basically rearranged terms so that I have this I e to the ix dx. And in doing so, I can basically backwards substitute and rewrite this integral as the line integral over the unit circle gamma of 1 plus 1 over z squared, z squared plus 1 over z squared, z cubed plus 1 over z cubed, dot dot dot, z to the m plus 1 over z to the m dz. And just to emphasize, this substitution is valid because I've basically substituted e to the I theta, I've substituted z in, and so I e to the I theta d theta becomes a dz, okay? And yeah, I guess I'm using theta instead of x, but hopefully you understand the idea of what I'm getting at here. And so now I just have a line integral of just some meromorphic function in the complex plane. And we know that the line integral of over a closed line, which in this case is the unit circle, gamma is the unit circle, this line integral is either going to be 0 for any term that isn't of the power 1 over z, or it's basically going to be 2 pi I times the coefficient of 1 over z in this expression, okay? So really what we're looking for is any surviving 1 over z term, because if 1 over z somehow survives in this expansion, then the integral will be non-zero by the residue theorem. But for example, like if I just have 1 over z cubed or 1 over z squared, that will still integrate to 0. Okay, so we only care about the coefficient of 1 over z when it comes to evaluating a line integral of a rational function like this over the unit circle. Okay, so let me erase some of this stuff. Erase page. Okay, so let's look at this integrand. We have 1 plus z to the negative 2 times z squared plus z to the negative 2, z cubed plus z to the minus 3, dot dot dot, z to the m plus z to the minus m, okay? And I want to know for what values of m does a 1 over z term survive. So I'll give you a couple minutes to pause the video and try to figure this out for yourself. Okay, so hopefully you were able to make some progress on this. So a good way to start is just to expand this first term. So expanding this first term, we find that we're going to have z to the minus 4 plus z to the minus 2 plus 1 plus z squared. Okay, and then I'm multiplying this by z cubed plus z to the minus 3, dot dot dot. Okay, and so immediately I see that for the case m equals 2, which is this term here, for the case m equals 2, I do not have a 1 over z term that's non-zero. And so the case m equals 2, like we predicted earlier, is going to be 0, which is a good sign. So now multiplying in for m equals 3, if I multiply in this next term, z cubed plus z to the negative 3, I'm going to end up with z to the minus 7 plus z to the minus 5 z to the minus 3 plus, ding, 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 z to the negative 1 plus z cubed plus, and I believe we might have a factor of 2 somewhere here, z to the 5th, and I believe I'm missing like some sort of factor of 2, and I think it's actually for the 1 over z term. Yeah, because we're going to have z cubed matching with z to the minus 4 and z to the minus 3 matching with z squared. So yeah, there should be like a 2 here. Okay, but that 2 doesn't actually really matter because we only care if this term is non-zero. And it is in this case. So for m equals 3, the integral is non-zero. Okay, so m equals 3, boom, the integral is non-zero. And now instead of like doing this brute force by hand for, m all the way to 10, we can try to recognize a pattern. And so we only care which exponents survive. So you might as well just keep track of the exponents. So in this case, the exponents for m equals 3 are negative 7, negative 5, negative 3, negative 1, 1, all the way to 5. okay? And when I multiply by the exponents of the next term, which is 4 and -4, essentially what I'm doing is I'm taking every number in this set, and you can think about this on your own, taking every number of the set and multiplying by z to the fourth will add 4 to each number, multiplying by z to the -4 will subtract 4 from each number in the set, and so I'm basically taking each number of the set, I'm adding 4, and then I'm unioning that with the set where I've subtracted 4 from every term. And so this becomes, for the case m equals 4, this set of surviving exponents becomes -11, -9, all the way to 9, okay? Where I'm just incrementing by 2 each time. And so you'll see that actually -1 is within this set as well. And so m equals 4 is also a non-zero integral. Okay, and so to generalize this, if I set am be the surviving set of exponents of surviving terms in the integrand, then a sub m is equal to a sub m minus 1, as we discussed earlier, plus m union with a sub m minus 1 minus m, where this subtraction addition is term-wise, okay? All right, and so using this method, it's very easy to calculate which sets are going to have -1 in them. And so it turns out that for m equals 3 and 4, the sets will have -1. Once I step up to 5, it's going to vanish, and then it'll still be gone in for 6, but for 7 and 8, we'll have -1 in the set. And it's very, very basic to verify this on your own. You just start adding like odd and even numbers, and you kind of see a pattern between, you want this set to be all odd numbers. And so certain, once I add and subtract 5 to this set, it's going to become even. Adding and subtracting 6, it'll stay even. And then once I add and subtract 7, it'll become odd again. And adding and subtracting 8, it'll stay odd. And then it'll go back to even. And so every time that it's odd, we're going to have a -1 in that set. And so -1 is within a sub m for m equal to 3, 4, 7, and 8. All right. You can verify this by hand or kind of using the logic that I basically hand waved around. But the point is that since the coefficient of 1 over z is non-zero, exactly for m equal 2, or sorry, not 2, 3, 4, 7, and 8, we know that this is our solution, okay? So then Im is non-zero for these m, and that's by the residue theorem. In any other case, we're going to have no 1 over z term in the integrand, and so complex analysis tells us that this integral here has to vanish identically because it's only equal to 2 pi I times the coefficient of the 1 over z term. All right, and so that solves this problem A5, and I hope you enjoyed that. Have a nice day.